Hi, everyone, and welcome to this month's Modular community meeting. We have a pretty exciting agenda for you today. We're going to start with a talk from Bernardo about porting GSplat kernels to Mojo. And then Seif will be giving a talk about hyperloglog in Mojo. And then to close out the community meeting, we're going to have Brad and Dennis are going to be giving an overview of the Mojo vision and roadmap documents that we just published. And then we'll be following with a Q&A about those documents. We'll also have Q&A for everybody's talks. We want to thank everybody for being here. And with all of that, Bernardo, why don't I turn the screen over to you and we can get started with your talk.
Yep, sounds perfect. So let me just share my screen as well. Hopefully you can see my screen. Can you just confirm that you can see the screen? Just so I have...
Yep, we
Yeah.
can see it great.
Perfect. So I'm going to be talking about Mojo Splat as presented. Essentially what I'm doing is it's more of a side project. I wanted to try Mojo and port the GSplat kernels or the 3D Gaussian splatting kernels to Mojo, and of course try out this PyTorch Mojo integration. So first of all, I just opened the repository today, so feel free to go there. It's very much ongoing work, and not all the kernels are implemented yet, and there's definitely some problems, and I'll talk about them because I think we can all learn from these problems. So just more or less introduction to the field of neural rendering. This is going very fast right now in research. Essentially, what we want to do is we want to render efficiently photorealistic environments. How we would usually do this in the past was we would have these polygon meshes, for example, what you have in video games and in big film studios, and you're rendering these polygons and everything, and you're trying to make as realistic textures, and the more polygons you have, the better resolution you have, and the more realistic it looks. But this doesn't scale very well. And we also want to have this learned representation, basically. We want to learn this from real images or from data instead of just having to have thousands of people working on one bottle or a scene for a video game. The prominent approaches are NeRFs and 3D Gaussian splatting. NeRFs came first, and then last year, or I guess a bit over a year ago, 3D Gaussian splatting came about. And 3D Gaussian splatting is the one that I'm going to talk about, but NeRFs is still very relevant, and it's came before 3D Gaussian splatting. So yeah, these are opposed to the traditional polygon-based meshes. So again, this novel view synthesis problem, we start from real images. We then try to optimize this 3D representation. Some of you may know photogrammetry, for example, could be an option, but still works in meshes and it's a bit messy. So we want to optimize a 3D representation that's light and easy to work with. And then we want to render new views, views that we have not seen or that we don't have images of. So use cases, of course, gaming is a typical one. I mean, Gaussian splatting is growing very, very fast. So you see this already in game engines or for video productions. This case, for example, a screen that projects a 3D environment that you want to render in real time to be able to record. It's a very good use case because you want realism, but you also want really fast performance. More prominent for me or more interesting for me is the research in autonomous driving. So in autonomous driving, you want to be able to do a closed loop simulation. So you want to be able to basically test your system without actually going out there. But you want realistic images and realistic sensor inputs. This is very hard. You would normally have to hire thousands of people to, again, design these 3D environments with all the details and as much as possible. This is not feasible and not scalable. So what most companies do not right now is they trying to use this Gaussian splatting or these representations to basically get from real data, construct these 3D scenes, and then simulate new views and be able to simulate going places where they didn't go in the original data. So this is from some colleagues of mine, where we have one sequence, but then we modify it, test different paths, for example, going around the car on one side, going to the other side, and be able to basically, I'll put it one more time maybe, be able to basically have infinite amount of possibilities with a 3D representation that costs barely anything to do. It's just we acquired one data and then we just reconstruct this 3D scene basically. So yeah, now comes the fun part, 3D Gaussian splatting. I'll explain a bit overall what it is. It's basically uh, replaces the nerf implicit representation with an explicit representation. As the name indicates, is a Gaussian splatting, so it's like projecting Gaussians, 3D Gaussians into a 2D image. So we try to, maybe I'll say this is very, very fast in rendering, but basically we represent a 3D world with millions or thousands of 3D Gaussians. And then basically what we do is we project these Gaussians into an image and we get the supposedly realistic image. So each Gaussian, for example, has a color or some way to calculate the color, has a size, an opacity, and a rotation. And this is kind of how it looks. So a normal Gaussian would be this green shape in 3D. And what we do is we then project it to a 2D plane, which is an image, and then we get, hopefully, if we have millions of Gaussians and they are well defined, then we get a realistic image. So I have here, for example, an example. This is a realistic Gaussian scene. In this case, we're reducing the size of the Gaussians to showcase um, how many Gaussians we have. Of course, you wouldn't reduce the size. This is just done artificially, so we can demonstrate how the Gaussians look. But we start from a very realistic image representation of Gaussians, and then we're just showing you there's Gaussians everywhere. Um, so we have this. There is this GSplat library, which is a very famous library with CUDA kernels to perform these Gaussian splatting tasks. Again, it's tied to NVIDIA GPUs, of course. It's very performant, very well used, and it was my inspiration. I used it quite a lot, and I wanted to try to see if we could match the performance with Mojo and maybe solve some of the problems of the fact that it's tied to NVIDIA and the fact that it's very messy to develop in CUDA, let's say. So comes Mojo Splat, my first attempt, I guess. I started this a few months ago, before the summer, I guess in April, and then somewhere along the middle way, uh, the PyTorch integration came about, and it was quite nice. And I'm gonna talk a bit about how this works. So the goals was basically porting GSplat CUDA kernels to Mojo. My first thought was, how hard can it be? It must be a weekend work, and here I am, and it's not all ported, so. I guess it's not a weekend work. I wanted to compare the performance with the CUDA native kernels. Of course, enjoy multi-vendor support, be able to run in AMD GPUs and hopefully one day in my MacBook, so I don't have to continuously SSH into a cluster. Um, Also, I wanted it to be callable from PyTorch, so that's something that I've been trying a lot. And just to keep in mind, I'm only doing the Gaussian to image rasterization. I'm not doing any of the PyTorch training thing. That's another different project, maybe. Um, so yeah, so I'm gonna talk about the kernels because I think that's what people are interested about. So there's essentially three kernels: a projection, binning or tiling, whatever you want to call it. I think there might be question or oh no. A projection, there's a binning or tiling, whatever you want to call it. And then there's a third, which is the biggest and most interesting one, which is the rasterization kernel. So the projection, the name entails, we're basically trying to, we have n Gaussians, could be millions of Gaussians, in a 3D world coordinate frame. And of course, we just want to project them to a 2D coordinate frame plus depth. So basically, what we do is we basically project these 3D Gaussians into a 2D frame. We compute this 2D shape of the Gaussian, and then we basically need the depth in that coordinate frame to then sort them later. Um, in the end, we also end up doing a lot of filtering, so a lot of the Gaussians that are not in the frame just go away, basically. This also gets a bit annoying because you have to also transform covariances and compute 2D radii, and but essentially not anything out of this world. Then comes kernel number two, which is binning, maybe one of the most annoying ones to program. Essentially, what we're doing is tiling the Gaussians. So we have these tiles, let's say 16 pixels by 16 pixels, and we're getting which Gaussians contribute to these pixels, basically. And we want to say this tile has these Gaussians, this tile has these Gaussians, and we basically just sort this and also sort them by depth. So yeah, we're basically tiling the Gaussians and then sorting them by depth per tile. So each tile has a list of Gaussians and there's the order that they should be applied. This can be very annoying because we are allocating tensors inside the kernel, or most likely we go out and go in again. So normally we have two passes, one first one just to decide how big each tensor should be, and then we have a second pass which fills the tensor, which can be a bit annoying. Yeah, if you want, I can talk more about this. And then comes the last kernel, which is the most interesting one and the most significant in my opinion, which is the rasterization of these pixels. So now we have each tile has the Gaussians that are relevant to that tile that should be applied in that tile. And basically we then parallelize over 3 dimensions. So each thread is basically we divide threads in tile width, tile height, and pixels in tile. So each tile is basically one dimension, and then we have each pixel in the tile is one different thread. Um, so each thread takes care of one pixel essentially. So here comes the interesting part, and what I like is the how the code looks or how the algorithm goes, which is very simple. Each thread first loads one Gaussian into shared memory. This shared memory is shared within the tile. So each pixel essentially in a tile is loading a different Gaussian. Um, this shared memory, as a lot of you should probably know, it's very fast memory shared within a block. I'll go. I'll talk about this a bit later, but then all threads basically pick up these Gaussians that each thread loaded, and they add to their pixel or they blend to their pixel, um, and then basically they go back to point one and just do this all over. Each pixel loads one Gaussian. All of the pixels apply the Gaussians loaded by all pixels, and then load another Gaussian. Essentially, this is the idea. Why this is very fast is because this shared memory module is quite performant or makes a lot of difference. Since each pixel is only loading one Gaussian, but all of them essentially apply the same Gaussian, then we're reducing the number of basically memory hits by a factor of I don't know how much, but if it's a 16 by 16, I guess you can do the count. This is also why tiling-based programming and all these compiler-heavy GPU programming languages do not work. Like Triton, for example, I've experimented a lot with it. It's really hard to make Triton have this pattern or understand that there's a more efficient way to do it by using shared memory on each pixel, loading it, and that each pixel around it will have the same Gaussian. So you cannot force this on Triton, so it gets really, really slow. And that's also why, for example, PyTorch implementations are quite slow as well. Um, yeah. So challenges. I think I'll call it challenges and opportunities because I don't want to also bash on the modular team. I think they've done an amazing job, and I think I'm very lucky to have been involved in some of the fixes or report a lot of bugs, and I'm really fortunate that they have been fixed. But I think we can all learn from the problems and the weird applications, the weird application that this is, and the problems that come from it. Um, so first of all, I try to exclusively use layout tensors. That maybe was the reason why it took so long as well. I think it's a very ongoing work and very little examples cause a lot of problems. Sometimes, for example, passing around between sub-functions inside the GPU kernel is tricky. I have not found a way to do it yet. I would love to have help on that if someone wants to help, because I always get compiler typing issues between the functions. Um, also, like PyTorch custom op library implementation in Mojo is very ongoing work, from what I understand. There's a lot of sharp edges. It's also changing very fast, faster than I can change my code. So that has been some of my ongoing struggle. Um, and the main hinder for me right now for this application is that the compiler right now optimizes for shapes. If you understood the kernels after kernel number 2, which is the one that has binning, any change in either number of cautions or where you're viewing from changes the number of like the shapes for the third kernel. So because it changes the shapes, it causes a recompilation, and that's the depth of this basically. We cannot render, for example, moving vehicle because it keeps changing the shapes, and that causes some issues in or causes some recompilations. But I know this is ongoing work, so I hope all of these will be fixed very soon anyway. So hopefully the names will change. I think what everyone wants to see is performance. Unfortunately, the CUDA native still wins. I have not optimized mine to the level or for years like the CUDA one, so of course it's not as good. But we also see a massive improvement over PyTorch native implementations. So for example, this is just for the projection kernel. The rasterization kernel had a bug until today, and I noticed on it today, so I didn't have time to actually perform more benchmarks. But yeah, for projection kernel, we can see PyTorch, for example, tends to do quite badly to some degree. Then Mojo improves quite a bit, and the CUDA native even improves more. But I expect this to go down a bit. The rasterization kernel is the one that shows a bit more promise as well. I'll post them later in the repository if anyone is interested when I finish those benchmarks. Yeah, ongoing work. Benchmarking the remaining kernels, of course, further optimizations, and there's still a missing. The binning kernel I still haven't done in Mojo because I have a lot of problems allocating tensors inside the kernel. I was trying to do some clever magic to make it even faster, but I couldn't. So that will be ongoing work. And thank you very much. And if you are interested, feel free to contribute to the project, or it's a side project, so I'll take any contributions I can.
Thank you so much, Bernardo. That was fantastic.
Thank you.
Um, yeah, and and as Brad was pointing out, we had a hackathon earlier this year, and we were told that there really was no accelerated Gaussian splatting implementation available for AMD. So it's really exciting to see this work happening, and that it's going to be available across a bunch of different platforms, and that that you've been kind of like building this out. Does anybody from the audience have any questions? Going once, going twice?
Chris,
Yeah.
sorry for taking so long, but I made it.
Oh yeah, no, thanks, Seif. Yeah, thank you for making it. Um, Dennis has a question. You mentioned that you had difficulties working with layout tensors. Can you share more about what these issues are and have you captured them somewhere? Also, same question for dynamic shapes.
So,
Yes.
Bernardo, we don't have to go into the details. Just tell me how can I
Yeah.
learn about it offline so we can fix those, right?
Sorry.
I mean, can you tell us more now or maybe
Yeah.
offline? I'm happy to chat with you after the meeting to learn about your experience.
Oh yeah, of course. I mean, I must give a warning that when I started this project, it was still managed tensors.
Mhm.
So there has been a lot of evolution since then. So maybe I'm not totally up to par with the latest Mojo as well.
But that's the whole point. It should be easy to use. If you try to use it and it doesn't work to your satisfaction, the problem is not with you. The problem is with Mojo, right?
Yeah, the most problems I had is passing them around functions is almost impossible for me from what I could do. Then trying to slice managed
Uh-huh.
tensors becomes a different um, type, and then when you try to pass it to a different function, it's almost impossible because then you would have to have a very complex type. So any
Mhm.
manipulation you do on managed tensor or on layout tensors becomes a new type, and then it becomes really hard to manage or to pass them around. That was mostly my problem with it. Of course, also the having the unknown sizes is a problem, but that's
Mhm.
more a compiler problem than it is a layout tensor problem, I would say.
Mhm.
Um, Bart has a question. Can your program change the view angle of the camera live, or does it render once for a given view?
Uh, I'm gonna answer. I'm not sure if I understand, but basically you have your representation in Gaussians. You can render any view basically. Live, yes, if it didn't have to recompile. Right now it cannot do live, or it does live. It just takes a lot of time because every time you run it, the kernels will change the number of the shapes, and then the last kernel has to be recompiled, and that can take a few seconds. So that's basically the main hinder right now. But theoretically, yes. Once we can make the compiler not generalized to, or not specialized to the shapes, then yes, you can do it live. My guess, I think right now, the last time I tested with like full HD and a reasonable amount of Gaussians, we could see like hundreds of frames per second, if not thousands.
Yeah.
Yeah.
Okay, well, with that, we should probably move on to the next talk. Once again, everyone, give Bernardo a big round of applause. Thank you so much for your talk.
Thank you very much.
And now we have our second speaker for the day. Everyone, please welcome Seif Lotfy to the stage. There's actually going to be a little bit of change on the agenda. He's going to be talking about Mojo data structures for database development. And so welcome, Seif, and please feel free to take control of the screen share.
Thank you. So, just a second. I think this is it. Sorry for putting the company logo and shit like that, but I'm keeping this very open. So, yeah, my idea is a fast probabilistic Mojo, basic structures for the AI era. I didn't change the I forgot to change the title but it's still in the same realm. So basically, my name is Seif Lotfy. I'm the CTO of Axion. We're a observability company. We built our own database from scratch. Call our database in Go. Everything is serverless, and we're hitting all these limitations around not having SIMD, right? Not having SIMD support. When 80% of your 80% of our workload is in IO, but 20% is in CPU, because we're dealing here with trillions of log lines. I say trillions, I mean actual trillions of log lines. And Go has almost no SIMD support, and what you end up doing is you have to write C code and ABX and compile it, and C Go and whatnot, and the overhead, and like, of course, C is not exactly the most accessible language for most of my engineers who basically went from Python to Go. Very good with data structures, but when it comes down to writing SIMD optimized vectorized code, we're not there yet. So one thing I did is I started looking into different languages. I looked into Rust, etc., and I just Mojo felt like the best of all worlds for me, right? And the first way to learn about Mojo was to write data structures I'm very familiar with in Mojo and see how I feel about it. So yeah, if you don't know what a column database looks like, this is a column database. You can see the columns. For example, the first column would be a delta. You could do a delta encoding on time. That fits beautifully in SIMD instructions. As in the layout is just it's meant for that, right? The location could be a dictionary encoding followed by a run length encoding. Of course, all these things we have to do manually, and writing SIMD and then wrapping it in C, etc. We did see improvements, but we thought, okay, let's see where Mojo can take us here. And the predictable memory layout of Mojo, it supports exactly what we need here. And then you'll see it later. I can always say Mojo is at least as fast as Go, right? And that's a statement I can say out of experience now. Rust beats it in some aspects, but again, Rust is, I'm sorry again, not to fuel any things here, but it's an ugly language, right? It's not Mojo. It doesn't have the Pythonish syntax, etc. So, as I said, the Mojo gave us the vectorization up front. The syntax was easy, and we thought, okay, let's take it now to the next level. Let's try to replace different pieces from Go with Mojo, for the low-level features, basically. And before I dive into, what we did, etc., I wanted just to explain again probabilistic data structures. Are you guys familiar with it, or should I do a quick overview of what that is?
I think we've got a pretty diverse audience. It might be helpful to basically do a recap, short one.
Okay, awesome. So basic probabilistic, when you're dealing with, you remember when we used to say big data? Now when we're the age of AI, data is not even big anymore. It's insane. It's huge, right? So more and more people start using probabilistic data structures, and what they do is you start trading off accuracy for less resources. So basically, you can use less resources to do a count distinct, or have I seen this before, etc. The easiest example is, let's say you want to keep track of, have I seen some, I'm going to come to that example later, but keeping track of, have I seen something before, yes or no, right? And the good thing about these sketches are these data structures, they're meant for, they can be done for online replication, offline replication, and they're very stream friendly, right? And it's perfect for distributed systems, and it makes these data structures a natural tool for AI, where throughput basically matters more than absolute exactness. I'll continue. So, oh, sorry. Can I skip to the Bloom filter first? Okay, Bloom filter. So we started off with the first data structure I decided to work on is a Bloom filter. Now, what the Bloom filter solves is fast membership checks without storing all the data. Think of it of, have I seen this URL before? Usually you would hash that and keep a 8-byte hash somewhere, let's say in a set, right? And if you are tracking a million URLs or URL IDs, you'll end up with 8 megabytes basically, right? And there's other ways of doing this where you would trade off the size for the accuracy. So you say, okay, I'm okay with a 1% error rate. And then when you ask me, have I seen this before? I would go, definitely not, or maybe, right? I'll never say I've seen something that I'll never say I didn't see something and I actually did see it. So I'll never give you a false negative, but there might be a false positive, and you can control the data structure. You size it, and you did the number of hashes to say, okay, how can I control the accuracy of it? And basically, this is kind of the algorithm behind it, right? You take X, hash it, let's say K times. So the 4 parameters, you just need 2 of them, and you can derive the second 2 of it. So if you say I have and I know the maximum number of unique items I have, and I know the precision I want, you can derive how big your Bloom filter will be and how many times you need to hash to reach that accuracy rate. And then when you get item X, you hash it. In our case, let's say we hash 3 times, right? And modulo the size of the bit map that you have, and just you set the positions to 1, right? And then when you want to look up, you do the same thing again, and if all positions yield 1, it means you've seen it. If one of them yields 0, you might have seen it. If one of them yields 0, it means you definitely have not seen it, right? Because we have hash collisions, etc. And the way I implemented in Mojo is I did double hashing to reduce the cost of multiple hashes, and I used a bit array like the 64-bit aligned bit array for it. I added the Bloom filter codes here. So you can check it out. And I added another Bloom filter implementation to it. So there's a standard in there, and there's a split block Bloom. And the split block Bloom is a different implementation that's even more SIMD friendly. And I'll get to that in a second. So I then implemented that and tried to compare it against my existing Go implementation. Now, the Go implementation is actually written by Daniel Lemire, one of the most notable professors in the area of data structures and SIMD, etc. And I compared them against each other. I almost did a 1-to-1 implementation of it. And 10 million hashes, same false positive ratio, 1%. Basically, I'm okay with a 1% false positive ratio. No false negatives happened. And we ended up with, Mojo just, 2.5 times faster on ingest. The, the positive queries where something is found, it's 4.5 times faster, 4.2 times faster. Negative, so something that is not there, I was able to execute in 1.5 times faster, which is kind of makes sense, because if you're looking up something, the moment you see a 0, you don't have to continue your calculations, right? So Mojo in that aspect, so that was the big surprise we had, right? Like, oh shit, Mojo is actually, this is interesting. We wrote something in Mojo that's actually faster than what we have in Go already. So that was the first, wake up call for us. And keep in mind, like, we're not coming from the AI perspective. Our customers, though, are some of the biggest AI companies you can think of. Like, we have Luma Labs is one of our customer, Preya is one of our customers. There, we have a foundational lab that, I can't mention who they are, but we're talking here 25 petabytes to 30 petabytes in management in less than a year, right? So this is all of this inference logs, et cetera, et cetera. And I know some of them are looking to Mojo and using Mojo, but for us, it's like, okay, let's use Mojo for database development. Let's do systems engineering now, right? I know it's not what Mojo is designed for, but I hope you can humor me here, understand why it's exciting for us when we see performance gains like that, and say, okay, so it's easy to maintain, easy to work, and it's giving me performance improvements. And sorry, and then we wrote another probabilistic structure called a hyperloglog. Now, hyperloglog is something, it counts distinct items in a set, right? So without keeping track, so something like how many unique users click this link, right? Like this thing count in SQL. You don't want to keep a hash set and then do a count, because that gets too big, right? So you can use a Bloom filter for it if you know upfront how big it's going to get, but it also doesn't make sense. So use something called a hyperloglog. And the idea is it's a mechanism where you take a hash, an item comes in, you hash it, you take a part of the hash, and or like the first 6 bytes, or like usually 16 bytes, and use that to decide which position, which register you're going to put it in. A register is like it. Okay, sorry, let me go back. This is how it looks like. My bad. I think this is better for me to explain how this works. So you have registers. These are uint 8, right? It's a array of uint 8, right? And it's a fixed size. And what you do is you hash something. The leftmost, in our case, like the leftmost 6 bits decide, okay, you're going to write something to position 11, and then you read the consecutive 0 bits on the right side, and you know that for 3 zeros to happen, the chance of that, the probability of that happening is 1 divided by 2 to the power of 3, right? Something like that. And the idea here is that you use the harmonic mean across all these possibilities that you're writing in registry, because you always write the highest amount of consecutive zeros there. And you use that to count the distinct items in a set, etc. And the estimation error in my implementation was, let's say, in other terms, usually about 0.8%, right? That was kind of in most of my experiments. And again, you can merge this across streams, etc. The difference is that with 8 kilobytes, I can count up. Sorry, with 16 kilobytes, I can keep track of a distinct count of up to trillions, right? Whereas if I try to do that with a hash set or a set, I would run out of memory, absolutely run out of memory. But again, the trade-off is there's a 0.8% off, right? And it's useful when you do something like, how many people downloaded this app, right? A lot of stores will just write 10 million plus, right? I mean, if it's 10 million plus, you don't really care if there was 10 extra or 10 lower, etc. It's 10 million plus, it's the ballpark, right? And this is how we use it. So we implemented that. Just a second. We implemented that also in Go. I implemented dense and sparse mode. to be honest, the sparse mode is what I actually did the benchmarks on, because the dense mode was one I did the test on, which is higher counts. The sparse one I did not run the benchmarks on against our Go implementation. Now our Go implementation is hyper optimized. It's used by bigger companies like Cockroach, like Elastic, etc. This library itself, but funny enough, the hyper log on query it wasn't much faster. But on ingest, we still saw 26% gain. Again, in our world where we run query, like the query costs on our side might be a ballpark of 15 to 20K a day sometimes. Saving 2K, 3K, or even more of that, it's a lot for us, right, as a company. And we looked at Mojo again, so with the least amount of effort. And I'm pretty sure once people like you take a look at what we've built, you'll find all the little bits and pieces we can improve and make faster, or make even better. Like this is our initial try to work on this. So, sorry. Yeah. So now we have these data structures, and there's more of these data structures. There's a top K data structure that gives you the top 10 things, also in a probabilistic manner, under the condition that they are not uniformly distributed, etc. Ideally ZF distributions. And we can use all of these data structures to detect duplicates in the corpus, and how many URLs, did you see, and then first pass cache filtering. So in a RAG vector or DB pipeline, the Bloom filter can cheaply rule out non-existent IDs before slower index lookups and stuff like this, right? Have I already seen this before? We use it quite a bit actually to skip reading pieces of data or objects of data off of the object store, because we know for 100% that this specific block will not have our data, right? And we can keep all of this in memory because it's so tiny. It's literally very tiny data structures. So what's next for us, right? With experimenting, the next experiment for Mojo at Axiom, basically we were trying to see, okay, can we, and that looks really, really weird, I know, but humor me. I don't want to write C code. I don't want to write Rust code, right? And it's easier for me to produce assembly like this. So we're trying to see, Mojo already lowers the LLVM, so we can generate we can regenerate assembler and wrap it up in C and use it via CGO. And already we will see some improvements there on large scale data. And this is kind of direction we're trying to take. Again, we're not coming from the AI, and we're coming from an infrastructure meets query database path that for us, this is exciting. Now, of course, I'll have to stay with primitive types or simple types, right? Because I can't do really complex things. But one thing I learned working with Mojo is I learned to think in a struct of arrays instead of array of structs, basically. And with that, there's a very easy way of keeping the data struct, keeping the function simple enough to do what we like to do. So we're thinking of encoding now, writing all the encoding in Mojo and wrapping it up in Go. So these are new experiments we're going to look into soon. And a couple of things that we would need help with here is we had a hard time trying to measure memory consumption, like actual memory consumption throughout benchmarks, right? And maybe we're not very familiar with Mojo yet, but we could use some help there, and I will be coming back to the community more and more. The other part is, I think in the world of AI and LLMs, etc., I think if you're building anything AI related, because you're dealing with such an insane amount of data, I think it will make sense eventually to have a sketches library where there's Bloom filter, where there's hyper log, where there's top K, where there's count min sketches, like all these different sketches that are targeting different problems. Like the count min sketches one I didn't mention is to keep track estimated count of a specific stream, not unique not cardinality, like actually every time somebody hit it. So the difference between how many times did they see a video versus how many times was the video watched is not the same thing as how many unique people watched the video, right? So these are two different data structures that solve two different problems, but they're useful in general. And another thing is because all our queries run in Lambda, I mean, we can write it in Docker. Like the idea is over time is to remove the Go code completely and have more Mojo natively just run and remove Go from the query path and utilize that. And for that, it would be nice if we could easily deploy this into Lambda. We can do this now with Docker, right? For small experiments, but we can't write full-fledged things right now. But what we're trying to do now is at least inject binaries generated by Mojo into the Go path, basically, or into our Go language. And yeah, basically that is the three asks I would have or help I could use from the Mojo community to move forward. And yeah, thank you. Sorry if it was a little bit of a messy presentation. It's a bit different, I think, from what people expected, but we are really trying to, like from an R&D perspective, we're really trying to take this into, I want to be one of the first companies like we're doing this, using Mojo for database development.
No, thank you, Seif. It's actually a fantastic talk. Bill was pointing out in the chat that he thinks that this is the first recorded instance of a Mojo Go integration. And it's neat to see how the intrinsics built into Mojo, especially like the SIMD data types, really give a lot of affordances for being able to implement high performance programming. And it's awesome to see it out there in the wild and to be used. So thank you so much for that. Unfortunately, I think that, oh, go ahead.
I just wanted to say, like, the community has been fantastic. The help I've got on the forums has been awesome, right? I now have 2 more engineers who have jumped into the Mojo world with me, right? Everybody's and I'm talking not engineers. I'm talking on a VP level and a principal engineer level. Like everybody's like, okay, this is there's something there, and it's we were all there around when Go started coming up. We were around there when Rust started coming up, and I'm seeing something. I'm seeing momentum from Mojo that I haven't seen in a long time. That's why we want to be part of this more.
Oh, that's fantastic. Well, we will probably follow up with you and talk with you more about this because we would love to learn more about that experience. We have about 15 minutes left in the community meeting, and so I'm gonna ask that we take the Q&A to the chat and say if maybe you can answer those there. And I want to bring Brad and Dennis up for the final talk of the community, which is an overview and Q&A about the Mojo community vision and roadmap documents that we've just published. So please, Brad, do you want to share the document or do you want me to?
Is that visible? I'm trying to get the
Yep.
right fonts on here.
Yes.
Excellent. Great. So I'm gonna do a very high level overview of what we have for. We just have 2 new published documents that describe the vision of Mojo as well as our short and long-term roadmap for the language. And so I do want to provide enough time in the rest of the session to answer your questions about these documents. So I'm going to do a very high level overview of these. For a much more detailed treatment of the Mojo vision and roadmap, highly recommend watching Chris's recent presentation on this from our community meetup a couple of weeks ago. We uploaded that to our YouTube channel, and I'll link to the documents themselves. They're great reading, so please follow along with those yourself. So I want to say that, Mojo and the technology behind it, they're the bedrock for everything we build at Modular. We've built a vertical stack on top of this that represents our bet on a more scalable, easier to use foundation for AI and more. The Mojo Vision document that we just published at docs.modular.com describes why we built Mojo in the first place, as well as our philosophy around the language and its frameworks. So you can see the link there, but you can also just go to our Mojo docs and you can find it very easily. The Modular's stated mission is to democratize AI compute. Massive amounts of computing capacity are being built out right now. And the potential applications of all that weird and interesting new hardware extends far beyond AI. But that only works if there is an easy way to make the most of it. So Chris has a great ongoing series that he's been writing about the history of how our industry got to where we are. And in that series, we're just now starting to talk about what we're doing about this. So, one of the most common questions we get asked is, why did Modular build Mojo in the first place? At a fundamental level, like Modular has made a bet on an entirely different underlying architecture based on MLIR core for targeting heterogeneous hardware. And so we needed a language to interface with that as a user-friendly like interface to MLIR and to build our infrastructure on top of it. Now, I won't dive into all of the positives and negatives of existing languages, but we had to pick something that we were going to build on top of this novel architecture. And so we decided that a Python family language like Mojo was the right choice for us. So, there are some driving principles that have guided our design and evolution of Mojo to date. We chose a Python family syntax to be familiar to the users of the most popular language in data science and arguably in the world today. And we wanted it to be built to solve problems that we'd seen with AI kernel libraries ourselves, particularly as they've had to scale to more and more hardware, more data types, and this expanding matrix of different capabilities. We wanted to be able to get the full control over all aspects of the hardware that you're working on, whether that's CPUs, GPUs, or more. And so it's easy to focus on the surface level details of Mojo syntax as a Python but fast, but under the hood, we've made some big architectural bets. Mojo, for example, is built on MLIR core, a unique feature of this language that lets it address a range of accelerator architectures while delivering surprisingly fast compile times. Compile time metaprogramming in Mojo, where you use Mojo to define how Mojo is built, like attacks the scalability issues of the ever-expanding matrix of hardware, data types, and kernels. And then all of this is integrated into a state-of-the-art graph compiler for building and optimizing the gigantic computational graphs that are today's AI models. So how do we keep this language on track? There are infinite possibilities for how a language can develop, so you need to somehow maintain focus. A great driver for focus is to have a specific application in mind and design towards that. We have these applications in mind ourselves at Modular, and so we write tons of Mojo code ourselves every day. From that, like we've figured out like what we want to prioritize and what we want to work on and what's important to us. But we also have learned from like what's worked for other languages and frameworks. So finally, we've tried to use simplicity as a North Star when making language decisions, and doing things like avoiding syntactic sugar, deferring it until later to try to keep the language as simple as possible. So talking about the vision for Mojo, that kind of defines like where we've been and what we feel about the language itself. But then where's it going to go? So we've been doing a lot of thinking about, planning where we want the language to go, what features we want to have, and how we want to roll that out. And so we published a roadmap for Mojo that is, again, linked to here. I highly recommend it. It is very detailed. There's a lot of breakdowns of all the different steps that we plan for Mojo in the near term and long term for the language. And so we've broken this roadmap into a series of conceptual phases. Phase 0 is where we were until about, I don't know, midpoint of last year or so, where we're building out the basics of the language and its tooling, and then also started open sourcing the Mojo standard library. And in this phase, we learned a ton about the language and again, the open sourcing process. That brings us to phase 1, which is where we are today. And the focus in this phase is on Mojo as a high-performance programming language for CPUs and GPUs. That includes a range of features we prioritized for writing state-of-the-art computational kernels for modern accelerators, such as like powerful yet ergonomic metaprogramming. We've talked about that before. There's some must-have like core language components that benefit all Mojo users that we want to complete in this time frame. We've also started expanding on the performance story by starting to roll out seamless Python to Mojo interoperability to allow you to progressively replace slower Python code with higher performance Mojo code. And then we're also trying to make it easier for you to get Mojo and and improving the tooling as all around it. But as the language is maturing, it's time for us to start thinking about like how we indicate what is and is not stable, like thinking about what this means for the language. And so I think that's going to be an important theme in this phase. And then, I will mention that like we have been progressively open sourcing more of the Mojo language over time, and we believe near the end of like this phase one is the right time for the like completing the remainder of that open sourcing for the Mojo language. And so we don't have any like specific timelines that we've listed on this roadmap, but we believe that we are on track for like working through this into 2026. So we feel good about like all the items and so forth that have been spec'd out on the roadmap for this phase. So then looking to the future, like that's where we get into like phase two, where we start to expand beyond like what we were building out today, and looking to the broader use of Mojo as a systems programming language. This is where our roadmap gets a little fuzzier, in that we know that many of the broad strokes of what we want to do in this time frame, but the specifics aren't quite as nailed down and spec'd out as we have in phase one. Big themes in this phase include finalizing the memory safety model, building robust like asynchronous programming interfaces, and other like major components to expand Mojo's use as a systems programming language. And then we look into the distant future of phase three, where we begin to think about what it would make to make it even easier to bring Python code to Mojo. That includes dynamic programming features like classes and inheritance. We can expand, we'll plan to expand like Python compatibility. And we're even talking about like the potential for migration tooling to make it that much easier to convert over Python code to high performance Mojo. So for more details on what's in these phases, please do check out the published roadmap. I will say we plan to update it as we land features and get clarity on some of the later items as we get closer to them. So I'm gonna run through these really quickly. Like we have a lot of exciting stuff that's happening that's even updating the roadmap as we are talking right now, because the Mojo team is just cranking through a lot of features. But I'll just talk about some of these high level items. One of which, so we now have default method implementations for traits. So that just landed in the nightlies, and wow, is that going to let us delete a lot of code? So that's a fantastic advancement there. That's just rolled out in the nightlies. That was one of our roadmap items, so we're checking that off as we speak. We just published parts 1 and 2 of a very detailed journey in writing state-of-the-art matrix multiplication for NVIDIA's latest GPU architecture, Blackwell. So please do check those out. They're super cool. They're going to be full of detail, and we're going to expand on them over time. We're working on a ground-up rewrite of our Mojo VS Code extension that will unify the 2 current extensions that we have out there. It will do things like use the LSP in your project's Pixie or Python environment, and we plan to open source it. And so, like, I know there's a lot of excitement for this. We get asked a lot of questions about this. We'll announce when that's ready for testing and/or regular use, but I know there's a lot of pent-up demand for this. Now in our nightly channel, you can go and pip install Mojo. So there's now a Mojo package that is available for pip install. That is right now only in our nightly channel. We're going to soon bring that to PyPy itself. And so that's going to make it even easier for you to bring Mojo into traditional like pip-based projects, as well as add it for dependency for your own PyPy-based packages that you may want to have depend on Mojo to progressively include Mojo into your packages. Super basic support for Apple Silicon GPUs is present in the nightlies. Although like right now, all you can do is the very exciting thing of adding 2 vectors together on the GPU, and it is gated behind an environment flag. But there are details in the forum that I've posted for how to use this and how to try it out today. We'll do a more public announcement or a larger announcement as we get more functionality ready that you can start doing some actual real world things with this. And again, I highly recommend checking out Amir's presentation from our community meeting a few weeks ago on how this is all built out. So that's like kind of like been a quick run through of everything. Hopefully it's been an exciting view of where we're going with Mojo at Modular. Again, we're going to open it up to more questions here, go a little bit over to answer your questions. We opened up a lot in the platform over the last year. We're excited to see what you can do with it. We love contributions, and I've been told to remind everyone that we have great swag for when you merge your first PR. So I just wanted to bring that up there. And so with that, I can turn it over to the actual questions that I know people have asked about this roadmap.
Yeah, Brad, if you refresh the slide deck, we actually have a list of questions that are in the deck there that people pre-asked in the Google form, and we also have some questions in the Q&A section.
Yeah, let me bring that back up. Sorry about that. I think this is. See if I have the. Sorry, apologize. Make sure I have the right one open here. I think this is the right one.
Yeah, that should be it.
That should be it. There we go. All right. Plans to add file embedding to make the content available during compile time. I don't know, like Dennis, have we talked about like any advancements to like the compile time metaprogramming to include files?
Yes, so this feature has been requested. Yes, we definitely will have it because pretty much every modern language has this capability and it's useful in so many different use cases. I can't promise whether we do it right now, it will take a couple of months, but yes, that's definitely on the plan. And if you have a specifics, like you have an example or some kind of motivational example why you want this feature, please add it as a comment to the issue I just added in the chat. So that when we design this feature, we will make sure we design it to include your use case. Like for instance, there is a question whether this embedding should work in the parser or in the elaborator after the types are known. So like what is do you want a literal embedding or do you want to compute the name of the file using like alias? So there are some details. So if you add your use case, that will be helpful.
Roadmap mentions that the closure refinement is in progress. Is there any progress that is worth sharing with the community at this stage, or is the progress in early stage currently? Dennis, I know we're making some exciting advancements here. Anything you want to share?
I was just chatting with Steffi on the side. She's working on that project. So she's reluctant to share the syntax as of yet, but I think it's safe to say that sometime in October, there will be a forum post with a new syntax for closures, with a proposal, and then we can have exciting discussions about how to refine that syntax with all of you. Maybe we'll get there before October, but I'm not sure I can promise that. So right now, where we stand, we've unified those two closure implementations that Mojo have. So we now have 3 implementations. Old one, old 2, and a new one. And we are slowly changing the code in our report to use the new implementation. And once we understand that the new implementation is powerful enough for all of our use cases, then we can share it and like talk about the preferred syntax. But I think we are a few weeks away from the moment where we know that our implementation is stable and powerful enough. So please stay tuned.
Is there any plan to add an explicit tail call decorator similar to Clang's must tail attribute or Rust's nightly become keyword?
I saw this question a few minutes ago. I looked through our roadmap. I don't see this request, so please file it. Obviously, this is useful. But again, if you explain your use case, say, this is the algorithm I want to implement, and it's just Stack Overflows, that would be helpful for us. Because, you know, we have so many feature requests. So the best you can do is to give us motivation, why this is a good thing to have, right? What example it would enable.
Yeah,
But
and
definitely in the long run, of course we should have it. It totally makes sense. You're right.
And for feature requests like this, posting them to the modular forum is actually an excellent place to do that because it actually allows for longer form discussion. And then, you know, it gives us a place to have a record of like the issues that you're facing and the problems that you're trying to address. And then we can more easily turn that into user stories, which will then become features in, you know, that potentially can become features in future Mojo releases. And so please, we would love to have you take this to the forum and explain your use case and your details more deeply to so that we can kind of like see how that fits into the larger roadmap.
Thank you.
Totally makes my job easier because then I can just copy your examples over into a user story.
Connor.
Yeah, I just wanted to add. I mean, we probably haven't had a specific use case to add this yet, but I do want to say folks who are familiar with Mojo's ASAP destruction semantics, one of the benefits that's specifically been articulated why Mojo does that is to enable tail call optimizations in a way that destructors get in the way of in languages like Rust and C++. So we haven't had the motivation to do it just yet. People should definitely add examples of their use cases like Chris and Dennis were saying. But this is something that Mojo is absolutely geared to have. It's just a question of priorities and timing.
When is Apple Silicon going to get included in the NVIDIA AMD list? Perhaps I should be asking which hardware is next.
I know everyone's excited about Apple Silicon, but give us a little bit of time. I was just chatting with Kolya, who is developing it. Yes, vector add is working, but we just tried element-wise matrix multiplication and we hit a crash somewhere in the guts of the compiler. So there is some work to do, but we'll get there again. It's a matter of time.
Yeah.
As to what other hardware, okay, Chris, Chris Pratt, I'm happy to defer to you about the next hardware.
Oh yeah, well, I mean, I think that NVIDIA and AMD and Apple are kind of like at the top of the hardware lists right now. The thing that I wanted to add to this is, we've been really focusing on a lot of the accelerator features that are at, kind of at the cutting edge of development, and so so we support tensor cores on NVIDIA systems, and I don't know if Apple Silicon has anything that is like comparable to the kind of tensor cores. Maybe the neural engine might fit into that. But that means that there are going to be gaps in the implementations that we have, the high performance implementations that we have for particular algorithms. And so matrix multiplication may not be as highly optimized for metal as we would want it to be. But we really feel like this is a place for a lot of strong community contributions, because if you have an interest on having a particular kernel for Apple Silicon, that maybe requires that we've implemented with higher level, more advanced GPU features for NVIDIA and AMD that don't necessarily exist on Metal. And these are awesome places for the community to jump in and really make a huge difference in the support matrix that we have. So we're excited about the Metal support. It's still a little bit early, but hopefully you'll see a lot more improvements in the coming months.
Yeah, I mean, and we're leaning into releasing things in nightly builds, to putting them out there early to let people see them. So you'll see things get built up as we are working on them, and things will be partially functional. When we're ready with the functionality for Apple Silicon GPU support, we will do a larger call to action with the community, point out the areas where we could use help parallelizing, bring up in adding intrinsics and so forth. And do more about that. It's just not quite at that state yet for publishing it. Why is memory safety a concern in Mojo? Is it security, the ability to control memory leaks, or perhaps something I'm not thinking of?
All right. We don't have Chris
Yeah.
in here, right? But I mean, if thinking very far into the future, there is certain desire to get Mojo to the level where it's like alternative to Rust, right? And yes, if you want the language to be useful in embedded systems, in serious programming, somewhere outside of kernels, you probably need a memory safe language, right? It's a given now.
Yeah. I mean, I can speak to this a little bit. Like in a former life, I was a C++ programmer, and a huge part of my training for writing high performance kernels was about memory and just about deep knowledge of ownership of objects, making sure you don't overrun bounds, and having and I know that that's improved in C++ over time, but having these features built into a language and built in a performant way, I think it lowers the barrier to entry, to, change how, instead of, programming being like turning you into an accountant of who owns the memory and, how do you access it and how do you access it safely and securely, into focusing more on how do I adjust memory access patterns to be able to, send memory to the different GPU cores the most effectively and to increase performance. And, and then we can build features on top of that to be able to manage that more effectively. And so really it's about taking the burden of the low level things you formerly had to do to write high performance kernels to more of the what are the high level abstractions you have to have in place to write the high performance kernels. And it's really about enabling future developers and taking away what's usually been a huge burden and often a source of pretty serious bugs in these kernels.
I want to say that in my domain, basically, you don't want, especially on the right path of data, you don't want corrupted data, and memory safety and ownership actually gives you guarantees that this will not happen. Else you'll, just have corrupted data. It doesn't make any sense.
I think it's maybe worth saying that like I just added that. I mean, part of Modular's vision is not just about, making a little bit less painful something that you might do in CUDA. It's about bringing people into this domain that maybe would have thought, like, that's not for me. I couldn't do that, right? And part of being able to credibly tell that story is when you come in, you don't accidentally run into kind of the low-level issues, low-level errors that make systems programming kind of have a reputation for being difficult or scary. So I think having an answer to how do we make Mojo memory safe while retaining performance, but feel easy, feel like you're being helped along. That's really important for the adoption story and for just people to have a good experience with the language. Like a minor thing, like I remember there's a surprising number of people who learned Rust coming from JavaScript because Rust gave something, the ability to write low-level code to people who'd never done it before. We want to do that for AI. We want to do that for kernel development.
And you're doing a great job at that. Like I would say, like I do have some Rust engineers, I have C engineers in my company, etc. And the moment they start seeing the performance that Mojo gave us, but with the simplicity of the syntax, and actually it made sense, right? We're not like it. I think that was the big thing. It made SIMD more accessible for everybody, for the Rust engineers as well as the Python engineers we have and the Node.js engineers, right? So you're doing a great job at it, by the way.
Awesome. That's great feedback.
What is the next big thing coming to Mojo as a language feature? Well, I mean, for one thing, you can go to our roadmap. You look at like we've got a lot of like unchecked boxes in like even just the phase one that we're in right now that are pretty important things. And so there's some real exciting stuff queued up there.
It's actually very explicit in the roadmap because we have closure refinement, requires clauses, conditional performance, struct extensions, and linear types, all marked as in progress.
Yeah.
And so one of them to make it first. Let's do something, right?
And if you want to follow along too, like if you're really interested to see what's coming out, I know that like the nightlies kind of land and it may be a little opaque, like what's happening in the nightlies, but we actually publish our changelog to the docs and we publish the nightly changelog. And so you can get a preview of like all of the things that we're excited about in that document, which will be kind of like featured in whatever in the latest releases. So, like one of the legendary features that we're planning for the 25.6 release is default trait methods, right? And that's like right there at the top of the changelog. We keep that up to date, and that'll be updated every time we send out a new release.
One little feature that maybe flew under the radar recently was I've been pushing on kind of resolving issues related to implicit copying in Mojo. And this is something that was largely framed as kind of it's a bug fix or an optimization, but it does actually change kind of the character of Mojo a little bit. So that's one big thing that landed recently that maybe didn't get a lot of fanfare.
Well, that looks like all of the questions that we have. If you have more questions, please take them to the forum. We have an event in the forum for this. If you have questions that we want to follow up on, you can ask there. We'll be sure to answer them. I want to thank Bernardo and Seif for giving their talks today. They were fantastic, as well as Brad and Dennis for giving the overview and roadmap. And thank you to all of the community for joining us. And we will see you in the forum and next month.